So now we're going to go back to our packet and we're going to prove the vertical angle theorem. By the way, just to mention, we are skipping over the linear pair theorem, which is on the page before it. Okay, prove the linear pair theorem, because we do not need to prove the linear pair theorem. We have assumed the linear pair postulate. We're accepting the fact that if two angles form a linear pair, then they are supplementary. We are not requiring ourselves to prove that. That is something we're taking as a postulate. So we can skip directly to the vertical angle theorem on the next page, and you might want to be writing some of this proof into your notebook because it runs rather long and I'm not sure if you'll be able to fit it onto the bottom of this page. So for that reason, I'm going to be putting it on a separate sheet of paper. So let's take a look at what we're trying to prove. The aim is to prove that vertical angles are congruent. And this is something that we've just accepted and we've worked with for quite some time, but we've never actually proven. And today we're actually going to do a formal two-column proof of that fact. We're going to do it in this specific case, which can generalize to any case, but in this particular case, we've got two lines that are intersecting, ZV and WY, and they're intersecting at point X, and they're forming two pairs of vertical angles. So we're going to look at one of those pairs, which is angle VXW on the top and angle ZXY on the bottom. And given that these two are vertical angles, we are now going to prove that they must be congruent. Okay, we're going to have to go back to some reasons that we learned way at the beginning of the class in the very first unit. So let's first write down our givens. So angle VXW and angle ZXY are vertical angles. So this is a given. Okay, let's go on to what can we determine then? Well, recall the definition of vertical angles that we gave at the beginning of the year. Vertical angles are angles whose sides form two pairs of opposite rays. Okay, their sides form two pairs of opposite rays. So that means that ray XW and ray XY must be opposite rays, and also that ray XV and ray XZ must be opposite rays. So let's write those two statements down. So we've got ray XW, remember how we draw the symbol for a ray, a one-sided arrow, and ray XY are opposite rays. And this follows from the definition of vertical angles. We also said that ray XV and ray XZ are also opposite rays. And this too follows from the definition of vertical angles. Okay, so we've gone so far, but I want you now to recall another definition that we used at one point, the definition of a linear pair. So the definition of a linear pair, the original definition was two adjacent angles whose non-common sides forms opposite rays. Okay, so let's take a look at what our diagram is showing us, and what we can see here is that XW and XY are pairs of opposite rays because of the definition of vertical angles, but that means that WXV or VXW along with VXY must be a linear pair because these are two angles that are adjacent whose non-common side consists of opposite rays. And by the same reason, angle VXY, this angle on the right, and angle ZXY, this angle on the bottom, are also linear pairs because they're adjacent angles from the diagram, and their non-common side, ray XV and ray XZ, are opposite rays. So let's go ahead and make these statements then. So we can say that angle VXW and angle VXY are a linear pair. And this follows from the definition of a linear pair, like we just discussed. And like we just showed on the diagram, that also means that angle VXY and angle ZXY are also a linear pair. Again, because of the definition of linear pair. Okay, so let's recall that we also learned something, and we just mentioned it a few moments ago, the linear pair postulate, which says that linear pairs are supplementary. So we can then say that if these two angles are a linear pair, and these two angles are a linear pair, then these two angles are supplementary to each other, and so are these two angles. So let's go ahead and make those statements. So if VXW and VXY, if angles VXW and VXY are a linear pair, then we can say that angle VXW and angle VXY are supplementary angles. And this is by the linear pair postulate. Okay, and we can also say that these two angles that are a linear pair are also supplementary. So angle VXY and angle ZXY are supplementary too. And that is also because of the linear pair postulate. Okay, so what does it mean to be supplementary? It means that their measures add up to 180 degrees. So let's go ahead and use that definition of supplementary angles to continue on with our proof. So, angle VXW and angle VXY are supplementary. That means the measure of angle VXW plus the measure of angle VXY is equal to 180 degrees. And that is the definition of supplementary angles. And similarly, we can say that the measure of angle VXY and angle ZXY add up to 180. So we can say the measure of angle VXY plus the measure of angle ZXY adds up to 180, also because of the definition of supplementary angles. Okay, so we've gone a long way, and we've got two equalities, both of which have 180 on the right side. So I think you've seen the pattern before. We're going to go ahead and we're going to set both of these left sides of these two equalities equal to each other through using either substitution or transitivity. So we can say now that the measure of angle VXW plus the measure of angle VXY is going to equal to, I'll stagger this a little bit to fit it on the same line, equals to the measure of angle VXY plus the measure of angle ZXY. Okay, and that is because of either transitivity or substitution. You can take your pick as to which reason you want to use. Well, we're in the home stretch now, because what we're going to do is something that you've seen before. We're going to use the subtraction property of equality to separate out a common measure from both sides. We've got the measure of Vxy on the left and the measure of Vxy on the right. So we're going to simplify this quite a bit, and we're going to end up with the measure of angle Vxw equals the measure of angle Zxy by the substitution property of equality. We've been able to subtract out that other common measure. So this is SPOE. And let's look back at what we needed to prove at the very beginning. We needed to prove that angle VXW was congruent to angle ZXY. And what we've got here is the measure of angle VXW equals the measure of angle ZXY. So we're done. This implies, or this, we can then conclude that VXW, angle VXW, is congruent to angle ZXY because of the definition of congruence. Or the definition of congruent angles, which is that their measures are equal. So let me write this out a little bit larger, because this is our important conclusion. Angle VXW is congruent to angle ZXY, okay, which was originally what we needed to prove up here. And since we proved it for this pair of vertical angles, and there was nothing particularly special about this pair was just like any other pair would be, and we could use any other pair in its place, we've basically proven the theorem in general.